If you can't solve this LeetCode problem, you're definitely cooked for interviews, so lock in. Today we're doing LeetCode 104, maximum depth of a binary tree. The depth of a binary tree is the number of nodes along the longest path from the root node down to the furthest leaf node. So in this example, the answer would be 3 because the longest path from the root node down to the furthest leaf node, which could be 15 or 7, contains 3 total nodes. Now, whenever you see a problem like this involving trees, you should consider using recursion to try and split the problem into simpler subproblems. And whenever you're using recursion, it's always helpful to think about the base case first. That is, what's the simplest case that this problem can be broken down into? The answer to that is an empty tree, because in that case, we simply return 0 no matter what. Now, for the recursive case, if you still haven't figured it out, think about if we start at the root, what information do we need from these subtrees, and based on that information, what can we return? What you have to recognize is that the height of any given node is equal to the maximum of the heights of its left and right subtrees plus 1. And if that sounds confusing at first, just bear with me. So if we start with the root, we want to get the height of the left side and the height of the right side. And because we're looking for the maximum depth, we just take the largest of those two values and add 1 to it. So in code, this is literally 4 lines. Our base case is if the root equals null, we return 0. Otherwise, we recursively call max depth on the left child and then the right child, and then return the max of those two values plus 1. Let's trace this through the original example. We start at the root 3, and we know that our height is equal to the height of the tallest child node plus 1. Again, since we are currently 1 level higher than both children. So first we call max depth on the root's left child, which is node 9. Node 9 isn't null, so we skip the base case and call max depth on node 9's left child. Now this value is null, so we return 0 back to node 9, which then calls max depth on its right child, which is also null, so we return 0. Now node 9 knows that the maximum depth of its children is 0, so it knows that its own height is 1, and it returns that to node 3. Now in node 3's function call, the original one, the call to max depth on root.left is finished, and it calls max depth on root.right, which is node 20. Node 20 then calls max depth on its left node, 15. 15 will call max depth on its left and right children, which are both null, and return 0, so 15 will return 1. Then 20 can call max depth on its right child, 7, which will similarly return 1, and 20 returns the max of those two values plus 1, which is just 2. Now we're back to the original function call for the root, and we've gotten the left subtree's height, which is 1, and the right subtree's height, which is 2. And we know that our max depth is the max depth of our left and right subtrees plus 1. So we return 2 plus 1, which is 3. The time complexity of this solution is O of n because we have to visit every node in the tree, and the space complexity is also O of n because every recursive function call allocates memory for a new stack frame. So in the worst case, if we have a completely skewed tree where the number of nodes equals the height, then we will have n active function calls at the most.